Or she comes in though.
Is
It's
anybody
supposed to be
doing-
like 95 degrees and nobody can see stairs.
You'll get so
huh?
tan.
Yeah. You can come back.
Oh my god, oh my.
Which like that,
I wish you could take that
and
moment.
it's a
Try.
Are we done with
Yeah.
Alright, bear with me, you guys, today's gonna be a little bit rough. I don't feel too good. I think my lunch got me. I already feel the sweating coming in at me, started talking. I put flashcards out, because we got low attendance. I don't have a quiz for you guys today. Table comes down. Either write down a quick summary of what's the key point or the pathway that you saw today. Put your name on it, put today's date, and I'll put it as your quick points. Yeah, so,
Awesome.
either summarize it for me, before we finish today, or, something that you think's unclear, and then I'll bring it up as my first point on our next section.
Just a
Yeah.
I mean, just a summary of the.
I distribute things.
Alright, so wait, no, so you guys remember I had messed up the order of the presentation, so last week we actually went over acting. Alright, so. There, the big things I want you to get, and let me hit them real quick, is that acting, right? Two types, you can have a blocker, which is free floating, or once you say yes acting, now we go back to the film. So remember, it's subunits, they can come together, we can basically make a cable, right? This cable, we can mess with it by putting different proteins that interact with it. A big one that I'm gonna bring up in this lecture is this R23, which helps us make these branching. You get a cable and you kind of build off a tangent, you can promote the mesh being built up. The other one is we can put proteins on different sides to do different things, right? Coffin, I want you to be thinking like a coffin, so it kills things, this is the one that binds in the middle of the fiber, you can split it, make it kind of fall apart. So coffin is the killer of the actin. Other ones you can have plus ended, minus ended for proteins that bind across the middle of it, all of those help stabilize it. Right? So by controlling these molecules, we can actually end up regulating actin. Yeah? Pretty good idea? All right, cool. So now, with that being said, we're gonna get a little bit into cell migration, but we're gonna keep in the back of our minds how this actin filament is gonna be playing its role. So for cell migration or cell movement, we're gonna look at a few different little windows. Embryonic development, the immune response is always a really cool one. Talk a little bit about wound healing, and we're gonna get into, we might glance over cancer metastasis. But I'm gonna focus on, you guys are gonna notice immune response in the movement is one of my favorites. It combines a lot of the sections together. All right, so the goal we're gonna be looking at, basically imagine we're looking at a single cell and we wanna see it crawl forward, right? In order to achieve this task of getting that cell to move forward, we're gonna need things like, you're gonna be able to deform the plasma membrane and stretch it out and give indication where we wanna go, right? So that's one force that we need to apply. The other one, it's a little counterintuitive just because when we live in our world, we kind of have it, which is friction and gravity. It's like if you put your foot down, technically my foot isn't glued or attached to the ground or anything, but just friction and gravity is holding me in place, right? And that allows me to be able to do relative movement where I can move my leg forward, and then now this one has that grip to the floor. At the cell level, you're gonna be looking at these little guys up here, which are gonna be like focal adhesion points. So as a cell, it kind of finds ways where it kind of grabs onto it. Because of that, it's able to push its membrane forward, grab onto it again, and it pull itself forward from each one of those interactions. So we're gonna zoom into this, we're gonna see what's going on there. The other part, as you're grabbing onto those points and the cell's putting itself forward, it's bringing its back forward. So we're gonna also look at what's happening with the cell, like it's behind her, the front of the cell, right? You need another behavior that needs to be working on that side, making sure you're keeping your cell intact and you're dragging it forward with. Right, so pushing forward, gripping to the floor, and then putting the back end in to keep it together. So we're gonna dive into those guys today. Should I do it? Might give me a little breather. Just kidding, guys. I'll change the video up. let's go. So now we're imagining instead of looking at the side view of the cell moving forward, I slice the guys right through it and we're looking inside the cell. And here we're imagining this cell is trying to travel in this direction, yeah. So for this, again, let's look at the task that I said we had to accomplish, right? Which one of them is, we need to be able to move our leading front edge of the plasma membrane, we need to push that forward. So that we're gonna achieve it in two different ways. One of them is this lamellipodium, which you're gonna see is, in this region, you have this enrichment of the branching, right? So again, before I said, ARC-2-3 helps make branches. Here you're gonna have a bunch of ARC-2-3 that will make your actin branching, right? That's gonna give you that force to push things forward. You can also have things like filopodia, which would be something like this. In that case, you're making your actin filaments, you're putting them right next to each other, and you're making them grow together in the same orientation. And that's gonna be the force where you can make like the small, like thin-like projections that kind of pop out forward. Sorry, that's filopodia. And then the last one we're gonna be looking at could be your stress fibers, right? And your stress fibers are gonna play into two of these things. One of them is these little gray dots would be your focal adhesion. So in my head, I'm thinking it's like my feet kind of gripping onto the floor itself. And what you do is you're basically connecting those with fibers to things further behind in your cell. And as these fibers, you contract them, you're basically gonna be able, since this is not moving, you'll be able to pull the other thing forward, right? So it'll be something like, imagine this is all my cell. I'm gripped forward, and because that's not gripped, when we pull the fiber tight, it'll make that section basically slide forward. All right. Cool. So now, we're looking at those three tasks. We're gonna super zoom into this, and we're gonna see how we're controlling this behavior to happen. So again, we're looking at the leading edge. This is the side that we're pushing forward. We're trying to get in the direction that we're going. And you're gonna see the big key players coming into play again, right? So first one we have is Formin. So remember, Formin was the one that helps you start to build up your actin filament, right? So it's one of the ones that promotes getting from not having anything at all, and you start putting at least 2 or 3 of them together, and then you can make your big longer chain. So, right, in some of your stories, Formin, critical player, we need it at the front so we can make the actin cables. Next, that ARC-2-3 complex, right? Look at this beautiful guy right here. It looks something like, should look something like this, where it's like you have a cable growing, it'll clamp onto a pre-existing cable, like at a side of a cable, and then it'll basically let you build another actin cable shooting off to the side. The more you do that, it'll look like tree branches, right? Like here, you have your cable with ARC-2-3, you'll split that way, you can ARC-2-3 again. 2-3 one more time. This one keep going, and you got a new one there. And as you're doing that, right, you can imagine this thing's gonna keep branching and branching and branching. All those cables at this end are gonna give you that big force. We're gonna move that plasma membrane forward and change our shape. On top of that, so that'll be the thing moving forward, you'll be building this thing. But remember, actin is very sensitive to concentration, right? If you imagine at the front of the cell, we're investing all our actin to make these cables, eventually we're gonna start to run out, it's gonna mess up our dynamics. So in that case, this is where this guy's coming in handy, coffee, right? Remember coffee, remember it's the killer. What you normally do is coffee, you'll start to express it near the back end, right? And the goal is, once we have this mesh pushing forward, you can start to destabilize the back. This thing keeps growing. As you shred these cables, they release themselves. Then you're gonna have profilin grab these actins, which now should be ADP bound. It'll give us that it'll work with that exchange factor, almost like a gap, but it does it with GADP. We bring in a brand new ATP, we kick off an ADP, and you reset your actin to be that ATP actin. Right? So it's like, so moving forward, I'm building the cables on this side, let's say. Back here, I'm releasing ADP. Profilin is going to remake them into brand new ATP actin, and I can use it up front. So the moving forward is kind of how I'm doing this, like taking old stuff, putting it in front, and kind of helps me move forward. Yeah. I'll show you a video. There's one I saw. It was a cool dude with a racing, and he's walking on bricks, and he's moving the little bricks to walk forward. and it looks just like that, it's gonna be funny. So yeah, at this point, we can sever stuff in the back, we keep building towards the front. By combining all those tasks is how we can have the dynamic of where we wanna push forward, right? Wherever we have foreman, where we have R23, we're gonna build, right? Wherever you have Coughlin, that's where we're gonna destroy stuff, so we wanna keep that away from the leading edge. And then Profit is gonna basically help us to reset these old molecules to bring them to the front to be brand new functional stuff. Yeah? This would seem like a good story, guys. So if we zoom out, instead of just looking at one cable, now we look at a bunch of these cables, right? So that would have been the initial one, there's your R23 starting to branch. And you can see here more and more R23 giving us this branch-like network. At that point, you can imagine your plasma membrane was at this height. Like that's where the cell ended. As you put more R23 out here, you put more more R23, more branching, you get more active. You can then start to dissolve this older molecules, right? You don't need them anymore, you just need the front ones to keep pushing forward. At that point, you cut the back, these molecules that got released as ADP actin, you're gonna modify them to become ATP, and you're gonna be basically pushing them forward. So you'll literally have your cytoplasm like, almost having like streams out of actin just flowing to the front, so that it can keep building the cable and you keep the front edge going. So for example, let's say, like quiz question stuff that I would like is, this process has to keep happening over and over and over again, so we can always have a good supply of ATP actin, right? We always need to have more of this guy, so we can keep building. If, for example, like what would happen if we lost our Coughlin protein? Right, and it is in the system, if we're trying to move the leading edge forward, all of a sudden, mutation happens, you no longer have Coughlin.
I guess it would just not be able to keep extending because the ADP, the ADP would not be able to go back to the profilin and keep the chain going.
All right, yeah, put 2 points on your paper. If you don't need questions, you're good. All right, how about if profilin, you mess up profilin, you don't have it anymore.
Overabundance of ADP in the cell, or of the ADP bound actin instead of the ATP, and like they'd all be the globular ones.
Yeah, so you'd be stuck right here with a bunch of these ADP. Beautiful. All right, let me get Gavin. What would happen, Gavin, if I accidentally make a mutant, but instead of breaking Coughlin, I make a crazy amount?
It starts making more. You would have an overabundance of the ATP bound actin, and your strands would get longer, and they would eventually get to the point where they can't function properly because you'd have too much.
Not that. Coughlin. Crazy amount of this guy.
Oh, I thought you were out
I know, I mixed it up. I switched too fast. Coughlin.
too much Coughlin. Then there wouldn't be a good balance in between like ATP bound actin getting brought to the front, and you would eventually, the amount of extra Coughlin would cause the ADP actin to basically speed up and catch up to the front. You would eventually run out of ATP bound actin, and then we wouldn't be able to continue the chain anymore.
Yeah, because you basically just keep shredding stuff forward and forward until you run out of cable.
Yeah, and if you have more Coughlin than profilin, then it would eventually catch up, and you wouldn't have any more ATP bound actin.
Exactly. All right. Both of you guys do the same thing. 2 points on your game. 2 more questions. I'll give you more. Yes, okay. Everyone else make sense? Yeah? Did anybody disagree with them? We did it school, we can argue. Question?
Just in regards to the quiz question, you just wanted us to do like a pathway in general or this particular one?
I'm hoping that the questions in your paper could be about today. If you want to do a summary of what we learned today, or if they have a question on today's stuff, I'll bring it up next on Monday, on Monday I will bring up the answer.
Okay, so like summarize something from today.
Yeah, if you summarize this pathway for me, I'll be more than happy.
Okay.
Yeah. But I'm gonna do 2 more quiz questions today to the class, so also do it that way, I'll just throw it in there. All right, so this is the whole dynamics of let's push this thing forward, let's get the front plasma membrane to push. Next thing we're gonna be talking about is how their feet, basically, not the feet, I don't wanna say feet, but how their attachment points work. Like how do they grip onto the surface wrong to be able to apply all these forces? All right, so for this, we have to get a little bit into the extracellular matrix, right? So it means that between the cells themselves, they basically have a mesh of these different fibers that kind of, like in that tissue, hold that tissue together. So the big one for us there, it's collagen, right? I think a lot of people have probably heard this when they talk about cosmetics and about your skin and, it not aging. Collagen is that thing that's holding all the cells together, keeping your skin together, and that's when we're young, super tight. Start losing our collagen, the shape starts falling apart, we get a little bit of sagging and a little bit of wrinkles, right? So that's that big mesh holding the outside the cells, holding the cells together. Part of that is gonna be that they interact with different proteins and they're composed of different components. So it's like, here we're looking at the laminians, which is the protein complex. And that's the one that gives us like sheet-like projections. I think that's this should be this guy right here. Proteoglycans would be this guys, right? So you can see this is a mixture of, there's your protein chain and there's your sugar chain. These are gel-like because of their ability to hold a bunch of sugar. The sugar itself has hydroxyl groups basically sticking out, alternating every single carbon. Hydroxyl groups, remember that's the big thing about hydrophilic, means AKA it loves to do hydrogen bonds. So this gel-like thing is achieved because you have this long cable, and then you can actually bring in water molecules to basically glue themselves, or like, not glue, hydrogen bond with this thing. So that fiber, you fill it up with water, that's what gives you that plushy gel-like texture. And then basically the adhesion points is where we're getting the cell itself that's trying to travel, it glues itself into this network. There you can see it, the protein, we zoom into it, it has different ways to bind to different fragments. So integrin binding, collagen binding, proteoglycan binding, right? So this thing will be like on the surface of the protein, surface of the cell. These little domains are gonna act again, those very specific interactions, it grips onto the surface, right? It'll grab onto the sugar chains, it'll grab onto these peptides, but that'll be the way that it can anchor itself. So here now we're imagining that, let's say we had a cell. This is the inside of the cell, this would be the outside of the cell. But imagine we're cutting it sideways where, again, if I was that cell moving forward, this would basically behave like little feet, right? That's what's gonna be up onto the floor. In that case, here's your extracellular matrix, right? Protein with glycans, you have the integrins making that fiber, or your integrins are connecting to that fiber, it's that mesh. When you do that, these are gonna turn this like extracellular binding into, these are gonna be attachment points, so you can look there when in your actin, right? So this thing is gonna serve across the membrane, working onto the surface. On the inside, you're gonna be able to build structures off of this. And that's where your actin is gonna help you act like a cable which you can pull onto it, right? You put actin, attach it to a focal point, your actin, whatever else you attach it to, those two cables, you can put motor proteins, and you can pull those things toward each other. All right, let's do it. So just like that, we can see that would be your basically free-floating cell, and we're trying to get it to attach to something or to move in a certain direction. This is where you're gonna have that interaction start to happen, right? It can happen again. It's specialized to each different interaction, but once you get it to happen, you'll actually have it attached to that surface. That'll make it glue itself closer. You have other like transmembrane proteins that are basically gonna help you get that interaction to get like spread out on the surface. As it's doing that, you're gonna see that the cell's basically gonna change its shape because it's getting more and more of its surface to attach on something.
Why is it more advantageous for it to like flatten out?
It's a combination of all the work it's doing that's gonna make it cause that shape to happen. In 2 or 3 slides, I'm sure. Yeah, 2 slides, I'll show you how when we're achieving all those little tasks, we end up building that shape by accident. But all the tasks that we're doing about stretching, grabbing, and pulling, we localize them in specific spots, and that's what gives us the shape, right? So wrapping across the bottom, it's a way to attach itself to the surface. So I would compress this way. In the front, when you're trying to make your actin filament, it's giving chemicals that it senses that it's trying to go in that direction. So in that case, it focuses all the actin R2-3 stuff to make that mesh at that spot. It doesn't do it this way, like it senses the direction, so it won't like try to make itself like a fan. I think it also helps with efficiency, but the signaling is what helps you kind of keep it in going in that direction. And in the back, you're making a mesh of wire to pull back those fibers to basically kind of drag it up. So all those three forces together give us that shape. I'm not sure, well, I mean, if you kind of think about it also just moving roughly, it'd be like if I'm trying to walk through the table through you guys. If I walk like this, it's gonna be hard for me, but if I kind of do this, I can kind of like sprint through you guys.
Thank you.
Do you think that that shape kind of helps increase its likelihood or ability to bind to the integrin proteins?
That's another key point, yeah. You have a lot more attachment points. So when you're making that mesh, you basically have more places where you can pull yourself forward. It can pull itself forward by making more cables that it uses the myosin to kind of contract them over. Let me think. I feel what you said was a part of somebody's experiment where they were messing with them. I don't remember how they messed with them. I can't remember if they messed with the receptor itself. Like they took the transmembrane stuff, and they started messing those up on purpose by mutating the cells, or if they hit them with antibodies. The antibody would go, stick to the feet, and it was kind of like they would come in, attach at one point, and they would just look like they're floating around because they couldn't grab on. So that was cool. All right, so we got ourselves to attach. Now the next step is, in that crawling step, is to pull yourself forward. And that's where this stuff's gonna come back in handy, right? So at this point, we need at least one focal adhesion point. We're gonna need at least two opposite oriented actin filaments, right? Then we need to bring in that myosin. So in this case, myosin, we have two of them, they attach to each other, but they're moving in opposite, they move to the same side in the case that they both love to walk towards the positive end. But because we arrange them backwards, this one will walk that way, this one walks this way. So as they're doing that, rough analogy, right? So it'd be like, this is my focal adhesion point, so this guy, it's not moving, right? If the fiber's coming through here, it'd be hanging off like this. The motor protein is moving the cable this way, trying to get itself closer. On this side, its fiber is attached to it, but it is not fixed to the environment. As it pulls this cable towards this side, it actually starts to move. So if you're attached here, these two motor proteins pull the cables together, this side's gonna get to start sliding forward. Yeah. So, okay, you have to have movement, you need at least one focal point, has to be completely attached, right? That's gonna be what direction we're gonna move. You need two actin filaments in the opposite directions, right? Minus end to the right, minus end to the left. And then you have to mix in these myosins in different orientations, right? And this one walks that way, and this one walks this way, and that effect is you bring the things together. Pretty good? All right, cool. So I'm gonna hit the surface on this stuff. I don't wanna go too heavy into them because we've gone into looking at transmembrane receptors. You guys remember GAF and GET functions and like Rho GTPases, right? So they're the ones that they bind to a G protein. You can when it's GTP bound, it'll be active. GTPase gets rid of the phosphate group, and it like silences itself, resets, and you get the whole thing. Flashbacks, you don't have to go deep into them. The goal is when we have this signaling available, we can make it do different things, right? So here's a regular cell, and in the white, you're basically looking at the actin, right? So this will be how the cables should behave kind of in a cell that's not doing anything. We then can throw these three different signals, like Rho, RAT, and CDC42, and then you can kind of try to study how is that signaling affecting the shape of the cell, right? So in this case, you can see if we do Rho, You basically superinduce the system, you're trying to get the row response. You're gonna hit the receptor activates the signaling cascade, boom, when it gets active, we get this thing to build up. So we see these long cables actually being formed, right? Because it's a strong induction, we're getting the cables to build everywhere. This isn't how they normally work, right? This is ours messing with the system to figure out how it works. So row, we built a lot of the long cables. If we do rack, right? Where are we seeing? You see the huge accumulation across the front edges, right? So in that case, we can see we're building big complexes right at the surface. We're not building anything too significant in the center, right? And then finally, if you put CDC42, this leads to formation of like the filopodia with these things. You see all the little spikes? That's basically like those little feeder things that are trying to grab onto the extracellular matrix. And that's what gives it, filopodia, the structures. Yeah, so this will be the pointy structures, but they're the ones that we can also use for gripping onto the surface. So if I drew a cell, this is the next question. If I drew a cell like that, it's trying to go that way. Right? Remember, if it's moving this way, it's trying to do a task here, it's trying to do a task here, and it's trying to do a task back here, right? Where do you expect to find row signal?
The A, B, or C, like in the location is what you're saying?
Yeah,
BC. Wait, BC, like the region between B and C.
right, because the goal here is you're making those fibers, right? Those fibers are the ones that are gonna help us grab the back. We're gonna basically scoot the back of the cell forward. All right, so here's where we're looking at our rows. All right, clear on your card, you're good.
I just have a question. So the fibers get like shorter to get like to move the cell that way, like the back of the cell,
The cables don't get shorter,
but it's like,
they do that myosin trick,
okay.
right? So you're right, I'm being lazy. So if I did my little drawing here, it would look something like this. That would be the cable from here with the minus end, cable from here with the minus end, right? Myosin comes in right here, and then the other myosin there. And those two cables get pushed, they get pulled towards each other. That cable itself, it doesn't have any shrinking function that can help bring them forward, right? Like it doesn't have, like it's not like a slinky where you can stretch it, and then when it shrinks, it'll pull it forward. We don't have that kind of force. It all has to come in through that myosin, doing the walking, putting the cables together. Afterwards though, these cables, when they stop becoming necessary, you are gonna kill them off. So, in a sense, yes, they will eventually become short cables, but then shorting or shrinking or anything doesn't have to do anything with the mechanical forces bringing the things together. You guys can separate those two, make sense? Yeah. All right. We'll still gonna row back. Yeah. Where should I find the rack signal?
Okay.
Why?
So the binding, the movement. About it being, like, is that considered like the front of the cell?
Yes, we're saying that.
Yeah.
Because we're saying like the cell's traveling that way, so we'll say it's the front, for this drawing, we'll be, this is the back, yeah. So, what's going on there with the rack, what are we doing?
Isn't that where it binds to the?
Not binding, it, don't help out.
So doesn't it, so rack forms the podium, and that's kind of what's stretching forward, right, to help it kind of crawl?
So this will be that stretch forward. I can't spell today, guys. All right. And how about CDC42?
The bottom, EB. Because like it has to form spikes to move forward.
Yeah, so this will help you making the spikes. I feel like the spikes, I need to double check, I feel like the spikes are enriched with like, different receptors or the different transient proteins to help you grip. So I think, I need to double check, and I think both of you might be right. So Rhea and you. Right, Rhea? Yeah, my bad. Rhea? Put it on your thing, put it on your thing. I feel like they get enriched. I might be mixing them up, so I'm gonna double check, but yeah, as you activate the melanopodia and the filopodia, the whole goal is you wanna make this thing stretch out, right, and get it forward. But if I remember correctly, it's like in that motion when you're stretching out forward, the same thing is still the goal that you have to attach yourself at that point. That way you'll have multiple attachment points, and you build this longer mesh like this. As you make the mesh from each foot to each foot, you're gonna control attaching these, you'll pull this one forward, once this releases, you basically lose this stuff, and then you attach the next two. This is the next one on the list, it starts releasing it, and it pulls forward, and you keep doing that over and over. Having you grip, pull forward, having you grip, pull forward. Okay, again, put your points on yours too. Alright. So, just how we're doing this kind of mechanism of, in order to move forward, we have to push ourselves into the environment, grip to where we're, grip to that new place where we move to, and then we pull the back of our cells. Our immune cells do this to find bacteria when they're trying to kill something off. Also, after you have a wound, or like your skin gets separated, it has this like encoded behavior where your skin actually shifts forward or tries to stretch itself. So I don't know, I mean, whenever you guys cut yourself, right? See any cuts on your skin, eventually they kind of seal back up in that tissue, right? If we stained your cells and you actually saw them over time, you see that the cells actually shift into that spot, like they glide themselves there. And then as they're shifting forward and they're trying to close up the space, they end up building a thicker and more like a tougher extracellular matrix. Again, bringing in that glycogen, not glycogen. What's the thing called? The skin one.
Collagen.
Collagen. You're bringing it, bringing in collagen to help build that mesh, right? So whenever you guys, I don't know if anybody has some like cool scars or like a thick scar,
Yes,
right? When you feel it, right, you can kind of feel it feels different than the rest of your skin.
it's like softer skin.
And then I don't know if you noticed, like it's like when
It's like
you,
waxy and tough.
and that's the mesh being built tougher because those cells have to fill in that gap. So we don't get a nice even distribution of cells and mesh. They end up making a thicker and thicker mesh, and you get like thicker scars basically. The crazy one that I was looking into is us, because we're out in the environment, and when you're cut open, you're sensitive to infection. We have to do this fast. So we normally push a few cells, we're pushing cells into the environment, and they're all trying to set up that extracellular mesh, and that's what gives us the scars. But if you wound a baby when it's in the womb, like if it gets cuts, because it's in a sterile environment and the cells can shift over slowly, they're actually able to more evenly spread out the cells, and they get a finer mesh when they develop it. So a baby won't get scars, but we all get scars. There was a lady in my old school, she was trying to trick the immune system by changing people's sugar levels, like almost giving them diabetes to slow wound healing. It made less scars, but the scary part is you're more likely to get an infection, so gnarly stuff. So, I'm sorry, back to what I was saying. The cells have this behavior, they'll try to protect you, seal off the skin, but they're doing the same thing. If you put them onto a plate, that behavior will show off that in the plate, they'll try to spread out to take over the whole area. Once they cover the surface area of that plate, they'll slow themselves down, they won't be moving around that much, and they slow down their cell division because they filled up the spot. If you go back and you scrape through that plate, the cells that basically lost their neighbors or lost their partners and messed the matrix up, they'll actually start shifting it and try to refill in the spots. So when they're doing that, you're basically using a combination of these genes to get that event to happen, right? So in this case, let's see. If you haven't answered a question yet, I'm gonna give you guys the first aid on this one. Right? The cells are trying to do the same type of behavior. What would happen if we take out, let's say, row? Again, we have that plate, we divide it up, we have two clumps of cells on each side, and then took out everything in the middle. Normally these cells want to go in and cover up the area. But I'm a scientist and I took out row. I used my gene techniques and I took out row. What
You're
would
just
happen
gonna
is,
have the open wound, it's not gonna heal like with people, like you said, with diabetes, they're not gonna have the same ability to cover the wound,
correct, right? But how would that cell work?
messed up.
But it includes on like the shape.
Flat?
So if you took out row, are we hurting the front, the feet, or the back?
The back.
You're hurting the back. So at that point, you still have DA function. So what do you expect that's gonna do? Stretch yourself
Stretch it
forward.
forward, it's gonna be longer.
That's another difference to stretch out forward. Because you also haven't affected the attachment points, right? Your knee is still gonna be attached. But you killed with row, you don't have the fibers to just pull this thing together, right? So normally, that action of putting the back forward is what gives it that little bit of like the big butt, right? Because it's like the cables are bringing the cell and it gives it that little hump. So if we don't have this cable function being built up, the muscle thing, right, this whole thing's gonna be super stretched cell, attached thing. So you're right, I just wanted to go through those steps. So I did it before, put points on yours. Does that make sense to everybody else? Yeah? All right. How about if we took out rack and what is this one? CDC 42.
So rack helps with moving forward,
Mhm.
so it wouldn't be as elongated.
Right, you couldn't get this thing to push itself forward.
Yeah.
So that's not gonna happen, right?
Yeah.
Yeah, exactly. But I think. So what was it if. No, I think that'll be fine. The other ones, you know, I could say is like, instead of saying suppression, if I ever said, what would happen if I have too much of these, right? Like for example, eye contact, it's on. What happens if I superactivate row?
Would it be like overly like bulbous or get too large keloid scars, to get tall?
Yep. Normally, I'm only having this compression happen back here because the signal is localized, right? But if I went and I tripped that cell and I gave it row on the side, it would grab all the filaments like this. These would be putting these together, this will pull this will pull that, and this will pull that. You know, using all the compressions, I'm gonna keep it pushing out that next time. That's pretty good. Everyone feeling pretty good about this stuff? Yeah? Are you gonna connect it? And remember, the thing is, I love you guys to argue, so when you give me the right answer, afterward, you still gotta argue with me about why it's right. So, that'll be good. So you guys know more. No, if it was, I would answer, I'm just kidding. All right, guys, so do not learn this slide, do not memorize this slide. Just appreciate it. From last section, right? Receptors. Right? But, what was my color last time? What was it my class this time? Purple. What was did I have an ignore color?
Oh, red.
Red was. I'll put red in the back of this one. Please ignore it. If you weren't here, they're gonna get tricked, but ignore the slide, just appreciate it, right? Okay? Integrate is the thing that's feeding your surface and saying, hey, this is what we're grabbing onto. That's gonna activate those row gaps. That's what's gonna help us change the different dynamics, right? So this signal, when I'm saying like, hey, we have row at the front, I'm imagining all this thing is happening right here, and we can get the localized signal so we have it on this side, right? If you have an integrate, you know what you're talking about having how we're gonna have it. And in the back, the row, the signals activating, how we're gonna build up these filaments. So for this one, you guys should know it's that protein that wraps around them to make them stable. Super helpful back here. Cat proteins and tail proteins, super helpful back here. Yeah. And R23 should be sitting up here. All right, I think we're good for today, guys. Let me see. All right, any questions? All right, write your name. If you don't, if you feel something you don't understand that well, I'll give you 2 points for that, and then, whoever got extra points for that. Thanks, guys.
Yes.